Okay, this is section 2.2 on functions. Functions are a central idea of math. You understand that functions pass the vertical line test for each x, there's only one y. Concept. This subtopic will demonstrate how functions give us a language in which to create mathematical models that describe real-life situations. Models involve creating functions to represent relationships between quantities that can lead to a better understanding of how systems work. Mathematical modeling is a logical process by which you start with real-life problems and arrive at quantitative solutions using tools of functions. While you are learning about functions through various representational forms such as mapping, equations, graphs, reflect on all that mathematical relationships represent functions, or whether all mathematical relationships represent functions. Hint, the answer is no. Think about different ways to express one quantity as a function of another. How could you use functions to model real-life phenomena and make predictions? So the concept of a function. Relations are sets of ordered pairs or sets of data. Functions, remember, for each x, there is only one y. All functions are relations. So any set of ordered pair is a relation. A rule is essentially an equation that defines the relationship. Okay. Keep in mind, domain is x, range is y. We're all going to talk about, so we're going to talk about something called the codomain. So domain tends to mean legal x values or potentially used x values. With domain, you are not necessarily dealing with, um, we can't do square roots of negative numbers. That's not in the domain. We can't divide by zero. We can't take logarithms of negative numbers. Okay, those are kind of your main domain restrictions. But domain, oftentimes we'll think of domain as, restrictions within the set of real numbers. Okay? Domain could be whole numbers. Maybe the real numbers aren't meaningful. Your equation might give you real numbers, but then you'd have to round them. Like, we can't have 1.2 people. Your codomain, this is an important concept in some college math classes, is again, what's legal? The range is which ones are actually taken. But your codomain might be restricted to certain number sets like real numbers, whole numbers. Maybe it's natural numbers only. Maybe it's integers. Okay. Your codomain can be the real numbers even if your actual range is only real numbers greater than zero. Okay, so it's what restricted set does this come from? And what it actually is from might be less than the whole codomain. Relations as equations and graphs. Here we have the circle x squared plus y squared equals 25. And we can very clearly see that this does not pass the vertical line test. This is not a function. It is only a relation. You could make it into two functions, the top semicircle and the bottom semicircle, by solving for y. We'd start by subtracting x squared from both sides. And then we'd square root. And keep in mind that when we square root, when we impose it, it must be the plus or minus. So function number 1 is the positive case, which we don't need to write the plus. Function number 2 is the negative case. With the TI-84, you have to graph both of those. With the TI-Nspire, you don't really have to. So let's show you how to graph a relation on the Nspire. I'm going to add a graph. You can do this in a scratch pad as well. But the program one puts me into ask me what I want to add. So when I go graph entry edit, so your menu, graph entry edit relation of X and Y, and I can just type my relation in. Just using X and Y squared. The equal sign here is important. It's right under the control key. It's highlighted in red right now. And there's my circle. You can graph any kind of relation on this calculator. It's wonderful. It's just as good as Desmos for doing that. A function mapping goes from X to Y. This, where it goes from 1x to multiple y's, not a function. And you should have at some point seen, these bubble diagrams. This one, not a function because 3 goes to both 1 here, and I guess I just need to draw a neater second bubble. Three goes to both 1 and 5. So that one would be not a function. Mapping diagrams are something you can also have them show going from one set to another set. Function notation. This is the function notation you've always used. This is a little bit higher college level set notation. A function from the set of numbers x to the set of numbers y. Means each element in x maps to a single element in y. Okay. And we might say something like y, x, comma y exist within the integers, meaning the domain of x is the integers. The codomain of y is the integers. It does not specify that the range is all the integers. But y exists within integers is what it's saying. The range might not actually take all of this on. So a little history with this international mindedness box. There's a debate within mathematics regarding the time and history of when the concept of a function was introduced. It is commonly accepted view that the real notion of a function with use of coordinates was initially expressed clearly and publicly by René Descartes, thus the Cartesian plane. Coordinates. Descartes, Newton, Leibniz, and Euler. Euler is the Euler. It's Swiss. And other mathematicians of the 16th and 17th century contributed to the development of calculus. German mathematician Leibniz was the first to use the word function in his book, something in Latin. Leibniz introduced the words such as variables, constants, parameters years later. The Swiss mathematician Euler was the first to express function using modern function notation y equals f of x. Functions as graphs and mapping diagrams. Um, Determine whether this is a function? No. 3 goes to both 7 and 8. The fact that 1 and 4 go to 6 doesn't matter, but 3 going to 7 and 8 is the key, not a function. Example 2, however, is a function. Each x goes to only one y. In the past, you've learned about one-to-one functions. This is not a one-to-one because 2 gets its value. 2 in the output or the range gets a value from both 1 and 2. One-to-one would be each arrow goes from one to another, and they only have one, so they're unique. Um, this one, what's it actually asking me to do? It asked me to write the domain and range. So this is a function. The domain is what x's are actually there. 1, 2, 3. 4 doesn't go anywhere, so it's not part of a domain. It's important that you use when you do functions these curly braces, something like that. They don't have to be particularly nice, but 2, 4, 6 is the domain range. No, they're saying this is not a function because 4 is supposed to be in the domain and it doesn't have an output value. Okay. I was not interpreting 4 to be in the domain. They're saying the domain has 4. Everything that's in the domain has to have an output to be a function. Is this a function? The answer is no, for example, 4, because 3 goes to both 4 and 5. And then example 5, we already looked at it not being a function. A couple of notation things. In IB, you are allowed to use any type of notation. For this is set notation. This says x is a member of the real numbers. The vertical line is such that x is between 4 and 9, including 9. You can use this interval notation. Apparently that's an alternative. I find that screwy. I don't recommend using it. That's weird. IB will accept any correct notation. Okay. For pre-calc, I made you use interval notation. I kind of recommend using it. Okay, you should be able to find domains and ranges. As long as your notation is valid, they accept it. Okay, functions as models. Mathematical modeling. Okay, we're jumping to example 2. You've asked a team of architects to set up a model for the area of a window. You must consider the following design requirements. The window should be in the shape of a rectangle with a semicircle placed on top. The window should have perimeter equal to 30 feet. Draw a sketch of the window. Where x is the width of the window and h is the height. So the radius here is going to be x over 2. So express the radius as a function of the width, show that the height of the rectangular part can be expressed as the following. So we know that the perimeter is 30. And there's one x plus two h's going around the perimeter and a semicircle. X, so that's pi times 2 times pi times radius for a circle, and it's half of that. So it's 1 pi times radius because it's a semicircle. So, oops, I erased more than I wanted to. Now I need to go ahead and solve this. I want to get rid of my fraction, so I'm going to multiply by 2. I need to try to isolate h. So I'm going to subtract 2x and subtract pi x. I will divide everything by 4. I'm grouping it like that because the 60 divided by 4 gives me the 15. I will factor out a negative x, giving me 2 minus pi, no, 2 plus pi over 4. And I can see that equals h, and I can see that that is the same as this. Create a mathematical model that describes the area of the window as a function of its width, x. So, area equals the rectangle xh plus half of the circle. And I know h, and I can plug in. Minus, we'll make this a little neater. Can plug in the h that I just found. Or the one they gave me. Because they're equal. 1/2 pi r is x over 2 squared. If you want, you can simplify. I don't think you have to. Find the area when the width is 4 feet. We simply plug in 4. I don't feel like simplifying. Oh, it's not 2 plus h, it's 2 plus pi. I made a mistake here. 2 plus pi. Four over 2 is just 2. And I can simplify that. I'd use a calculator. And there is a basic mathematical model. Making connections. Linear models are used to represent how one quantity is a function of another. When it's a line, the change in the independent variable is constant with the change in the dependent. Linear models are useful, in, for example, in estimating the amount of time it takes to complete a round trip, where assuming traffic conditions are optimal and the driver is traveling at a constant speed. Banking institutions sometimes do simple interest, which is also a linear model. Theory of knowledge. The map is not the territory is a famous quote by Alfred Korzybski, which reminds us of the representative nature of models. Apply this quote to mathematical modeling. Can the same be said for mathematical modeling? Or do mathematical models differ from maps? knowledge question here would be what justification provides mathematical models with their certainty? So the idea that the map is not the territory, think about that. It's not exactly the same, but it gives us a guide. Okay, last thing we're going to do is inverse functions. Inverses undo. It's an important concept. Informally, the key to inverses. Let's take this particular function. I usually call it y because it's easier. The key to inverses is switch y and x. We usually then finish by solving for y. And if the inverse is a function, you can use this inverse function notation, f inverse of x, or it's not f to the -1 power, even though it looks like that. And that gives me my inverse. You should be familiar with inverse functions. If they're inverse functions, this is an important thing. If f of 1 equals 2 and g of 2 equals 1, if it does that for every point, they are inverses. Okay? A property of inverses. If f and g are inverses, so this is saying they go back and forth. That's one definition of inverse. Here's another one or a property that's helpful. If f are inverses, and this is going to go into composition, which is really the next section, but you've done before. Both ways of composing, they have to equal x. So inverses go one way and backwards. So we're going to find this one. We're going to go jump to example 2. And I'm going to go ahead and write it in y equals notation. If you're good at this, you can skip that first step. Now I need to solve for x.
Is there rock climb club this Friday?
No,
Okay. Cause Halloween,
no, because first and third Friday.
it was 2 weeks ago that we had rock.
First and third Friday.
Oh,
It's the last Friday of October. There happen to be 5.
oh, thank you.
Yeah. And the following week, there won't officially be rock climbing club because I can't be there. So when I finish solving, I get this. It asks me for f inverse of 5. So I plug 5 in. Fifteen over 2 minus 3 over 2 is 12 over 2, which is 6. We're talking about graphs of inverse functions. They are reflections over the line y equals x. So here we've got the line y equals x. Here are my inverse. We'll call that f of x. No, nope, they're calling this one f of x. And this one g of x, which is f inverse of x. So it asked me to do this as a plot. I graph the line 4x minus 2. I get that line y equals x. That there. Honestly, what I do is I switch the coordinates. That's how I start. So I've got 0 down here is 0, -2. So I go to -2, 0. This here is 1, 2. So I go to 2, 1. Literally switch the points and graph. So this is f inverse of x. Okay, that is section 2.2.